We have had already a few sessions where we talk about the arrangement of particles as they come together. This is called self-assembly. And that will govern the properties that emerge from the granular skeleton. So let's review those once again. For coarse grain fabrics, we took the extreme case that we had grains that could be either loosely packed or that could be densely packed. And we did computations of void ratios and pore size and the largest particle that could fit inside and that could fly through for filter criteria. We advanced that quite a lot, so go back and please take a look. Now, this maximum and minimum packing density can be captured for coarse grain soils in the following diagram that shows the essence of what determines the packing of coarse grain soils. On the one hand, the coefficient of uniformity, which is always misleading because the higher the number, the better graded the soil is. In other words, there will be smaller particles that can fit within the voids of the larger particles. So if I plot void ratio here, the void ratio will decrease with the coefficient of uniformity, and whether that is the minimum void ratio or the maximum void ratio. And that is why the coefficient of uniformity is such an important parameter in soil classification. But there is one more parameter that we tend to disregard for the packing density, and that is the shape. So as particles become increasingly more angular and less spherical, these charts show us that we have a higher minimum and a higher maximum void ratio. Summary: the packing of coarse grain sediments is determined by the availability of finer fractions within the coarser fractions to fill in the voids. And in fact, it could be a gap-graded distribution, which is used, for example, in many European codes. And it's also affected by the angularity of particles, which constrains the ability for them to rearrange to take lower potential energy configurations. So this is coarse. Then we talked about the arrangement of fine particles, and we highlighted the differences between 2-to-1 clays, the sandwiches with 2 silica tetrahedra sheets on the outside, montmorillonites, ilites, and the 1-to-1 sandwich, which is the kaolin, with an aluminum octahedral sheet on top of a silica tetrahedra sheet, and we have different phases, and they give us different configurations. We tend to summarize those by the possibility to arrange edge to face to face, edge to edge, or just dispersed. There is one more situation there are many more situations. Let's consider another one that it can be quite important in the behavior of sandy materials. And that is the case when there are mica plates mixed in with the sand. These are micaceous sands. And in this case, it will look something as follows. We're going to have the mica plate probably bridging over gaps, so increasing the void ratio on the lower side, and on the upper side, enforcing particle organization. Whenever we have an interface, we always have a structured pattern of particle arrangement for the first 5-6 monolayers. So micaceous sands, if we are able to zoom in and see the particles both the platy particles and the rotund sand grains, we're going to see these two effects: forced arrangement or preferential arrangement, and bridging and large voids. So this is the combination of mica and sand. Clearly different soil particles with different interacting forces and different grain sizes and shapes will lead to different arrangements. This will manifest at the very beginning when they self-assemble, and then as we increase the confinement and the packing develops and evolves. Then the question is, how will the fabric evolve during loading? And so we can think of several conditions, but the one that we are going to address next is when we load under zero lateral strain conditions, like in an odometer cell, which is the typical effect of burial as different sediment layers pile on each other. So the classical plot in this case is one where we're going to plot the void ratio versus the vertical effective stress in logarithmic scale. This is a misleading scale. If we actually see it in linear scale, the higher the confinement, the lower the void ratio, and that goes almost exponentially decaying. But let's stick to this scale for now. And we see that coarse grain sediments, let's say that we are starting with a void ratio of 1. Coarse grain sediments are going to be somewhere here, and then they're going to decrease and show some trends like that. And in this case, I'm plotting in logarithmic scale, so probably this is, let's say, 100 kPa. 100 kPa. This is 1 megapascal. This is 10 megapascals. Depending on the mineralogy of the soil, different processes take place. Here there is at the beginning contact slippage, and then as the stress begins to approach 1 megapascal, carbonate grains will begin crushing. Silicate grains, quartzitic sands, are going to crush closer to the 10 megapascal. But we can say that in this range there is rearrangement, while in this case we go into crushing and densification. But the range is not so pronounced. I forgot to say that if burial is taking place, and this is 1 millimeter per year, to reach 10 megapascals, this is going to be approximately 1.5 kilometers of burial, and for 1 millimeter per year, this has taken 1.5 million years. Now, when things are so progressive, other processes may be occurring. For example, if this was a carbonate sand during the formation, there may be pressure solution precipitation taking place, where contacts dissolve and reprecipitate on the shoulders, and there is a very significant densification. So it all depends the time evolution together with this stress increase. Now, when we look at fine-grained sediments, actually, because of their particulate arrangement, remember the edge-to-edge and edge-to-face, then they can develop very loose fabrics. And this is for materials where the specific surface area increases. And as you can see, the end void ratio can be very low, and at this point we may be in the case of shales, where the porosity may be less than 5%, and if you think of the high specific surface and you compute the mean pore size distribution based on void ratio on a specific surface, then you conclude that you are indeed at the scale of nanoscale pores. Now, this evolution of void ratio in the case of clays starts by the formation, which at the beginning was edge to face, face to face, edge to edge, etc. As burial takes place, particles begin getting organized in forming tactoids. And so those initial self-assembly fabrics rarely evolve to form tactoids, and you can see these bunches of particles behaving together. This is one of the most significant differences between coarse grain and fine grain sediments. Is the evolution of their packing with effective stress. Then there are several questions, such as what determines these asymptotic values of void ratio, both at low stress and at high stress. Let me address only the asymptotic void ratio at low stress. And if we plotted versus specific surface or grain size, this is the asymptotic void ratio at low effective stress. As a matter of fact, as the effective stress goes to 0, some materials may have asymptotic void ratios, like fine-grained sediments like montmorillonite, that exceed 10 or 20 void ratio. And if we plot versus specific surface, low specific surface means large grains, and here we're going to see a cloud of void ratios that represents the sands and silts, where this will be Emax as an upper boundary, and this is E-mean. As we begin moving into the range of fine-grained sediments, let's take as a nominal size 1 micron. This asymptotic void ratio at very low effective stress really begins taking off. So the maximum and the minimum void ratio of coarser soils, as discussed a few minutes ago, is determined by the coefficient of uniformity and the particle shape. And all the cloud of points that we have collected fall somewhere between those two, with the asymptotic void ratio at low confinement typically being closer to Emax. But depending on the formation history, for example, is it a transgression, an invasive oceanographic regime, particle shear by the currents may lead to fairly dense configurations as well. However, when we go into the small particle size, all the data points are going to plot between fairly characteristic fabrics, where the very open edge-to-face flocculation give us a very open structure, while dispersed fabrics tend to give us a much denser configuration. You can convince yourselves that this is the case if you choose pH and ionic concentration to cause the dispersed fabric, and a very a pH at the transition between 5 and 6.5 to cause edge-to-face aggregated fabrics in kaolin, and you just do the mixtures in test tubes, put in exactly the same amount of kaolin, you shake it very well, let it sediment, and you will see these asymptotic void ratios. In fact, the experiment that I have just described is a good way to get an estimate of what are the asymptotic void ratios for the beginning of what we call consolidation or self-compaction. You may wonder, where is the void ratio at the liquid limit? Well, we can compute that one because we know that gravity waves are produced by supernova explosions. So the void ratio for the liquid limit is equal to, at the liquid limit the soil is pretty much saturated, so saturation will be equal to 1. It's going to be equal to the water content times the water content at the liquid limit, which is the liquid limit, times the specific gravity. So if the liquid limit is 5, if the liquid limit is 0.5, 50%, if it is 0.5 times the specific gravity, which is 2.65, that void ratio is 1.3. And now we can draw the void ratio. The void ratio also has an association with a specific surface, and the liquid limit at the void ratio is going to fit somewhere here. This analysis tells us that when we start our consolidation curves and our compaction curves, we tend to start them at fairly low void ratios because we have already assumed that the soil has some degree of compaction. The actual limiting state for a soil as it approaches zero effective stress, which you cannot see here because zero cannot be plotted in a logarithmic scale, the actual asymptotic state is much higher. And one of the reasons why we start soils at the denser configuration, even when we do mixtures, is because those mixtures experience suction, and capillarity is already bringing particles together. You think that the soil is experiencing zero effective stress, but because of suction, the soil may already be anywhere between 10, 50, 100 kilopascals of confinement. The asymptotic void ratio at zero effective stress is an important parameter for understanding our soils.